I will get into the math now. So please ask any questions if you have while I teach the course. I hope that this can be as interactive as it can be. So the first chapter is on enzyme kinetics. And you must also already have some access to lecture notes that are typed. So there you will always find more details than the ones I will be doing in class. So if you want to do some extra reading, maybe it's a good time for you to start looking through that as well as I go. But everything that I will be covering in class is basically what you need. So if I don't cover something in class from the actual typeset notes, it means it won't be covered. OK? All right, so the first one is on enzyme kinetics. So if this is the first time you are taking a course in physiology, I first want to give you some background on this. So first of all, what is an enzyme? What does it do? Why is it important for us to study it? So enzymes are catalysts and what they do is that they help convert other molecules which are known as substrates into products. And importantly, so they do this. Basically, you have some substrate, you have some enzyme, it comes, it binds on it, and then it helps it produce these other molecules that are called the products. But the most important thing for you to remember is that enzymes don't get used up in the process. So you have an enzyme at the beginning, it binds to the substrate, and you get also a product plus the enzyme. OK, so I will make this point down. So, but are not used up in the reaction themselves. Is it visible to the people at the back? OK, perfect. OK, so some applications of this are in the digestive system. You can think about it. Basically, enzymes act on molecules to give you glucose that you use for energy. They can also be used in DNA replication or in liver enzymes to destroy basically toxins or other chemicals. So now how do we write this reaction mathematically? So if I tell you to consider two chemicals A and B, so consider chemicals A and B reacting. So they collide with each other to form some chemical, which I will denote by C. And I have to also specify the rate at which this reaction happens. So it will be with some rate K. So very simply, I can write this as A plus B. So this A letter basically denotes the concentration of this chemical A. And then I have a concentration of a chemical B. They react together under a rate K, and they produce C. Is it clear so far? OK, so when I have this, basically, I will also say here that the rate will depend on the size of your molecule. It will depend on the temperature in which this reaction is taking place, and also on the shapes, and so on. So now, you can write this as a differential equation for the process. And you say the rate at which this chemical is being produced, so this in dt, is proportional to the product of the concentrations of the two. And the rate of proportionality is this K. So I'm going to write down K, AC, AB. So this is what I have. So if I asked you, let's instead imagine I had another example, and I gave you that I had AB, but with an extra molecule, a larger concentration of A reacting again under the same rate to give me product C. Does anyone have any idea of how I can rewrite this using this relationship that I gave here? So now you have double the concentration, basically, of A. Yes. Yeah, exactly. Is that what you're going to say? Perfect, exactly. So you can write basically, this is going to be A squared. If for someone it's not that clear, and you're like, how can I know? You can just imagine doing A plus A, right? So you have A times B. So it gives you this. It's the same thing. OK, great.
Are we ever worried about the reaction volume?
No, because it's taken into the concentration, right? So yeah, you can have like more complicated things, of course, like dependence on the space and so on. But for the purposes of this class, for now, you don't need to worry about that. Yes?
Are there any constraints in K?
Yes, it's not going to be a constant. It's more complicated than this.
Or is it less than 1? Or is it, like, it's not a probability, it's just the rate?
Yeah, it's just the rate. There are no restrictions. OK, so actually, you will be asked more on this on problem sheet 1. So maybe I will write here PS1, question 2, so that you know to come back to this point. OK, this has a name. This is called the law of mass action. The law of mass action. And here I have made the following assumption. So we assume that the mixture is well steered. And what this actually means is that the concentrations of these reactants A and B that I talked about, the concentrations are uniform of, you can say, of reactants, are uniform in space. OK, congratulations, this is section 1.1. The next thing is section 1.2. By the way, this law of mass action will keep coming up, so it's important we understand it. The next thing that I want to talk about is this Michaelis Menten kinetics. So for now, this won't mean anything to you, but we will derive it together, and it will make sense, I hope. So now I will give you a more general case of an enzyme reaction and how it looks like. And then using the law of mass action, we will be able to derive some differential equations. And then not only we will be able to write down this model that describes the reaction, but we will also focus on how to solve it. And in general, this class is on developing the model and also solving it. So an enzyme reaction in general will look as follows. So I will give you some substrate with concentration S. And then with this, you're going to have some enzyme. Again, the letter denotes the concentration of this enzyme. And then I will specify that in the forward direction, when these two react together, I'm going to have a reaction rate of K1. And when the two react, they give me some product, which for now it's an intermediate step, which is called a complex. So I get some C. And then the C can also break down now with a rate of K2 into the enzyme, because I told you it doesn't get used up in the whole process, plus the final product P. So this is a one-way interaction. So you just have that the C breaks with this rate into E and P. But I have that this intermediate step, the complex, can also be broken down to produce the substrate and the enzyme, but with a different rate. So it's also a backward process. So here I will also have K minus 1. So to help you a bit with your notes, let me denote what these different things are. So this is what I call the substrate. This is the enzyme. Then this I will write here that is a reversible reaction. This thing is called the complex. And this final is the product. So it's a, basically I should write here, it's a two-step process. Okay, so if we actually want to think about this problem, you will see that if I want to simplify this, I can think about it as the substrate producing the P with some new rate R, right? With some intermediate things that I don't know about. So the overall reaction is going to be S producing P, we said, with some rate R. So you could model, I will write here, you could model the single reaction and capture all the intermediate steps with this overall reaction. This has a name. This is what is known as the Hill equation. And will also come up later today again. So now I will use this overall rate R, and I'm going to write it as a function of the substrate. So I have some initial rate R0, the substrate S raised to some power n, and then Kn plus Sn. And these are some constants. We will come back to this equation, so don't worry if it doesn't make sense for now. OK, so from this, you see that now that I wrote R, even though this looks really simple, that the substrate breaks down into a product with this rate, this is not a constant rate. It's something that's complicated, and it depends on my substrate and the overall reaction. OK? So now that you have this, and you also learned just now the law of mass action, we will be able to derive together what the system of differential equations is that describes this simple process over here. So from this, you should expect to have 1, 2, 3, 4 different differential equations, right? I should be able to tell you how the substrate, the enzyme, the complex, and the product change with time. And for that, we will use this notion of law of mass action. So I will use it on this board over here so that you have it in front of you. So it's better, instead of doing that thing with the Hill equation, to use the law of mass action. And I will go in the order that I have them there. So first the substrate, then the enzyme, the complex, and then the product. So let's write an equation down for ds dt. So you see here, so do you expect the S to increase with C or to decrease? And with what rate? Yeah, so what should I write down there? What do you think?
Minus K1C.
Perfect, because S gets converted to C, so it gets less and less, right, with this rate. But I also know that C can break down with this rate to give me S. So in this direction, it should increase it, right? Exactly, nice. So it's exactly what your classmate said, but notice that when I do one of these, like when basically S and E react together with K1, I get C, right? So in one direction, you have to be careful that the S is reacting with E. In the other direction, it does not, right? So I should get a product somewhere. So in this direction with the K1, I should get just that with plus because C gives me S. but in the other direction, I should have a minus, and then it's the product of S with E. Does that make sense? OK, great. So then I go to the next thing. So it's dE dt. OK, now that we have this one, what do you think this should be? So E in that direction decreases, right, to give me C, but it reacts with S. So what should be the first term?
Minus K1 SE.
Yeah, exactly. So it's going to be minus K1 SE, and then I get E produced with these rates for C. Because notice that you have the enzyme also on the very right-hand side. And then since you understood how to do this, I will write the other two down. So the complex basically increases when S and E react together, and otherwise decreases with these two rates. And then finally, for the product one is the simplest one. It basically increases with rate K2 when you have C being produced. So we have these equations. So I will name them 1, 2, 3, and 4 because I will be using these equations now. Were you able to follow? OK, great. All right, so my question now is, can we actually simplify this? It looks kind of complicated. We have 4 coupled ODEs. So we want to simplify this. The answer is yes, otherwise I wouldn't have asked. So yes. And the reason is that if you see P, basically, do you see P anywhere else apart from here? No, right? It's decoupled. So basically, once you manage to solve everything else, the C, S, and E, you will be able to plug it in here and solve for P as well. So you can simplify it a bit. So I will say here that the product only appears in 4. So it decouples. So basically, you just integrate 1, 2, and 3. And then once you have it, you can get the P. Now, we'll also point out the fact that if I add equations now 2 and 3, you will notice that, hopefully you see this, that dE dt plus dC dt gives you how much? These are opposite signs, right? And then this is the same, so it's just 0. So if I wrote this out, it will be d dt of E plus C. So what does it imply about E and C? It's a constant, right? It doesn't change with time. So I know that E plus C is equal to a constant, and I'll just name it, let's see, E0. Why did I name it E0? Because basically at the initial time, if you look at that reaction that I have over here, you don't have any of the complex at time 0. So you only have the enzyme. But it also tells us that the enzyme concentration is being conserved during the process. This is what this says. OK, great. So once we have this, then I can write that the system now reduces to this reduces the system to only 2 ODs, and I write them out for you. These are going to be the rate of change of the substrate, which is going to be K1 with the -1 C minus K1 S. The initial enzyme now, so I'm substituting for the E minus C. So notice that I did E is equal to E0 minus C to get this. And then I will also write down the equation for the complex. So for this one, we have K1S. It's multiplied by the difference between the initial enzyme concentration and the complex minus, and I have K2 plus K -1 C. So your system basically becomes this system of 2 ODs. And I will focus on solving this now. So of course, when you're doing some solution of ODs, you need some initial condition, right? So I have to tell you at time 0, this is how much substrate you have, and so on. And once you have that information, you can solve for the unknowns, which are the substrate and the complex right now. So I will write here, which can be solved subject to suitable initial conditions. So you might be given something else than the one I will give you now, but it will be straightforward how to extend it to that case. So for you now, I will just say that the initial substrate is S0 and that there is 0 complex at time 0. Whenever we are doing some analysis of these kind of problems, it's very useful to do also a non-dimensionalization of the problem, which means that you get rid of the units in the process to be able to infer something more generic, right? So this is the next thing we have to do. So I will say here now, I will focus on these two equations, and we will non-dimensionalize so this is an important thing to do, the system in order to be able to analyze it. OK, so the choice of non-dimensionalization, sometimes it's not unique. But for now, I'll just give you the non-dimensionalization we will use. So I will have that the substrate can be written as the initial substrate times some other variable, little s. By the way, if you have a question now when I'm writing it, if it's capital or not, ask me. And then I will have something for the complex as well. So this one will be based off on the initial enzyme concentration times a little variable c. And finally, I will also give you a new definition of time that depends on this new variable t prime divided by the rate of reaction times is 0. OK, now that we have specified this, I have to use these new variables now to rewrite the system in the dimensionless form. Right? So the way you do that, so you see here I have d in dt, for example, with the original time that has units. So I want to rewrite it with those variables and end up with something that is of the form little s and t prime instead. So this is how I will do it. So I have to use the following procedure. So thus note that if I want to rewrite this is the same as using this equation over here and this. Is this with little s now? And similarly, you can write down the dc dt. This is going to be the original enzyme concentration times dc in dt. And I'm going to have also the transformation of dt in order to plug it in here. So this will become dt prime. Here I'm just doing the differential of that. And then if you want to write it as d dt, you're going to end up with this instead. OK, so taking everything into account, basically this equation over here becomes, so I will take it that you trust me that I did the computation correctly, but if you don't agree, you can let me know. So you end up with this k minus 1 c. This is little c. And then I have minus k1, s0 s, 1 minus c. And I have some extra notes in the write-up that I will share with you later. OK, so this is how this equation becomes. We will do exactly the same with the second equation to write it in dimensionless form. But before I do that, let me simplify this one a bit. So if you see you have these extra things in front, so I want to get rid of them. So I will just divide through by k1 s0 to obtain. And I'm going to get now ds dt is k negative 1 This is minus 1. And then I have minus, this just drops off, so I have 1 minus c. Okay, so I will do some rearrangement here because I want to define some new constants that will become important later. But you can basically rewrite this as -1 k1s, and then I have minus the little s. And now I will introduce this lambda, which is just a new parameter. So this is the same as ds dt prime. Here, to introduce this new parameter, I will just add and subtract a term that is the same, so I don't change the equation. So basically, I will copy this thing down. K1 is 0, and then let me write it also with a different color. Basically, I will add K2 now. So K2, remember, is this. So I have K1 is 0. Since I added it and it wasn't there, I will subtract it. And then this is minus s again, which is this one. So the reason I did this is because this will become a parameter that I call lambda. And this will also be used throughout the model. It will be denoted as k prime. So let's write it out. So this k prime is basically, this is the same denominator. So I have k minus 1 plus k2 divided by k1 is 0. And I have defined lambda to be the thing after the minus. So it's basically k2 over k1 is 0. OK, so this is what we have for this. Now we do exactly the same for the c term. Maybe I will write it here. So again, use the same procedure that I did here to rewrite that. So the dc dt equation becomes k1 is actually e 0. And then I have dc dt prime. K1 is 0. And then I have the little variable, so it's 1 minus c minus k2 plus k minus 1 c. All right, so I will do exactly the same thing that I did here. So notice here, in order to get rid of the constant in front of this, I just divided through by it. Now I want to, despite the fact that I have E0 here, I will still divide by the substrate initial concentration. And there is a reason for that. There will be a small parameter, basically, that multiplies my derivative there. So we now divide, so again, by k1 is 0, like we did there. So now you will notice the k1, you see it goes away here, and then you get an extra term here. And then in front of the dc in dt, I will get E0 divided by S0. So I have just this remaining here, minus, and if you notice here, you see this is just this constant over here, right? So I have k prime. So this becomes k, is that clear? OK. All right, so since I have this, now just note down that this thing is a small parameter that I will call epsilon. So I will rewrite this equation basically as epsilon dc dt is equal to that. And you can also combine the terms a bit differently since you have c and c here to write out the equation in the following form instead. So this is the same as s minus s now. Since I have minus outside, I'm going to have a plus k prime, and this is times the complex concentration in the dimensionless form. Yes?
Is epsilon
Small. Yes, that's the whole point. Perfect. Exactly, because basically the whole point of showing this and introducing this small parameter is the fact that in order to have this big reaction to produce the product P on that side of the board, we need very little enzyme in order to do that. It's very efficient as a method. So the enzyme, you have very tiny amounts. They also get conserved during the process. And you can have whatever breakdown of toxins or whatnot using these enzymes with small epsilon parameters. Yeah, thanks for the insightful question. So I will state here what your classmate asked. So where this parameter epsilon, which is E0 divided by S0, is much smaller than 1. And this basically says that we only need a bit of enzyme. So it has a remarkable effectiveness, basically. This is what this says. All right, so now if I combine these two formats, what I am left with is this equation for the substrate, which involves, again, just the complex concentration on the substrate, and then the simplified equation for the complex. So overall, what you need to remember is these two equations. Minus S plus C, S plus, after having introduced this lambda. And then with the epsilon, I have dc. And we will see some interesting dynamics if we set this limit to 0. You can say here if you want, by the way, with initial, again, if I want to solve it, I need some initial conditions. And those should be for S and C. So I should have right, because I have basically S0, if you remember, and then from the non-dimensionalization that I just covered, I have this. So this tells you that the initial little s should be 1, right? What was the initial complex that I defined? Yeah, the initial complex concentration at time 0. Do you remember? 0. So little c at 0 should be also 0. OK, excellent. All right, so now this thing that your classmate pointed out before, that this is small, now leads to the following thing. We can say, let's look at the limit where this goes to 0. This won't go to 0, but the whole thing, since you multiply it, will go to 0, right? So let's see what happens in that case. So epsilon much less than 1 means that we can neglect the time derivative in the second equation in the C equation. OK, so basically this means that we have a so-called quasi-steady system. So a steady system would mean that it does not depend on time. Here, it sort of does. So quasi means almost steady system. So the reason we call it that is because S still evolves with time. You see it through here. But the C will not. It will be an algebraic equation. OK? So I will say here that S evolves through a time derivative. And instead, the complex concentration C evolves through an algebraic equation that we will actually derive right now. So if I look at the limit of small epsilon, what I have, as I said, is that this thing goes to 0. And so if I write on the left-hand side that, I'm left with this. So I'm trying to get an algebraic equation for C, which means that this is just C is equal to S over S plus K prime. This is just, if you remember, a sum of the two reactions divided by the other reaction rate. So it's just a constant, this K prime. All right, so this is an important part of the solution. And then now I will just take this C that I solved for, and I will plug it in here. That will leave me an equation for ds dt that just depends on the substrate concentration S. I got rid of the C, right? What type of ODE is it? It's a first order ODE. What methods do you know usually to solve first order ODEs? Integrating factor, right? Or separation of variables. In this case, it will be an integrating factor because you have the substrate concentration. OK, so let's do it together. So I will say here, if we plug in this into the first equation, ds d prime, we get, so I have ds dt prime minus s, and then I have again plus. So the C right there will be this. So I have s plus k prime, and then I have s plus k prime minus lambda. The trick here to simplify things, you just make a common denominator. So this will give me, this is little s by the way. When you just have a common denominator there, you end up with a simplification, which I will not write down now here to not waste time. But we have basically this. And I hope you believe me again. Just do this times that and just simplify terms to get this. OK, so I will denote again this equation by something so that we can refer to it. So this thing has a name. I hope I'm not butchering the pronunciation, but I think it's Michaelis Menten. And this is a law for enzyme kinetics. Do you have any questions so far? Yes?
Scenario summation that the enzyme and substrate can be possible to sign. Isn't that highly dependent on the reaction you're working with? Some reaction terms like that.
Yes, it's of course dependent on the reaction that you have, what concentrations you have initially for the substrate in the enzyme and so on. But in general, when you have an enzyme binding on a substrate, you have very small concentrations, like 10 to the minus 7 or something of enzyme compared to the substrate. So you can always make the assumption that the epsilon is really small. But yeah, the absolute values will change based on the reaction. Does that answer your question? Okay. All right. So now, how can I talk about this reaction rate now? So I will ask this question. What is actually the reaction rate? OK, what am I asking here is basically, if you remember, I have the product being produced as part of this reaction, the P that we had written down. So the reaction rate is going to be little r. This is a definition that I'm giving you. Is going to be the rate of change of the product in this enzyme reaction. OK, and this is, I'm going to give it to you, it's going to be minus ds dt. This is because it is more the state of depletion of the substrate. Remember that I don't have basically, if you remember, I wrote that the overall reaction was this. Remember, without the intermediate complex and so on. So I'm now saying that the substrate gets depleted with this rate to give me the product. and we will be able to derive an equation for this. So here, if I use the same exact non-dimensionalization that we looked at together a bit ago, I can simplify this into the following. So this is little s right now. This is s capital. And I will make a note here that this is due to the non-dimensionalization. But if you remember now, I just defined this Michaelis-Menten law. So this gives me exactly the format of ds dt prime, right? So I can take this and put it in here. So use the star from that board. So this will give me that R is basically this. Now let's substitute back S is equal to S0S, which is this non-dimensionalization. And I will also give you again the definition of lambda, which probably you don't remember because it was this complicated ratio. Is K2 divided by K1 S0. And then when we use these two things, we basically get the following. So I have that the R, the reaction rate, simplifies to the following. So there is a lot of intermediate steps that you can find in my notes. It's just a manipulation, basically, of simplifying a few of the constants. And then when you end up with this, basically, you have this new constant. This K constant is now defined as the sum of these two rates divided by K1. And this, again, has a name. This is called the Michaelis constant. Okay, so in general, you might have asked me now, but how do I know in my model what these K1, K-1, K2 constants are? How can I quantify them? So the way you do that is experimentally. So you will be given in a problem what this should be if you're asked to solve it for a specific problem. So it's actually not that straightforward to measure the constants individually. Reaction rates. So what people instead do is that they say, I'm going to measure the whole reaction rate, which is this little r instead. Okay, so instead of saying experimentally I can get what this K1 is or K-2 and so on, you say I'm going to start with this substrate and enzyme, and I'm going to get this product, and I know that the overall reaction rate is going to be this R, which I can't determine. Okay? So we can measure the overall reaction rate R and concentrations. So for this, of course, you have to be given again an initial substrate concentration, which is the S0. So if we look at the initial rate of reaction, meaning I have not R of t now, since this is a function of time, but I have R0, the initial one. I'm going to write it as K2 is 0 S0 divided by S0 plus K. And then from this, we have 2 more minutes, so I can finish this. So basically what I want to do is look at 1 over this reaction rate initially. So this just becomes S0 plus K divided by this. I will again do, okay, let me write it out for you. This is K2. And here I will just simplify this. So you can just split this divided by that plus this divided by this. Simplify the S0 with the S0 to get basically the following. So I'm trying to write it in this particular form to point out something. 1 over, and I have S0 as well. Okay, so if I'm trying to plot a thing for this function, I can treat this now as a new variable. This is a linear equation for 1 over R0 in terms of the reciprocal of the initial substrate with a certain slope and a y-intercept. Okay, so just imagine this is y is equal to mx plus c. And when you plot this kind of thing, it has a name. So this is so think about this as the y-intercept and of this as the slope. These kind of plots are known as Lineweaver-Burke plots. And I will stop here for today and we'll continue next time. Next time I will also cover, next time meaning tomorrow, transion membrane transports. So it will be, again, a different application, but we will see more techniques for writing down differential equations and solving them. Thanks for your attention.